Let us continue our discussion on diffusion into an infinite medium, the solution using a similarity transform. Okay. So, if you recall, I had earlier solved the problem of diffusion into an infinite medium, a time dependent diffusion, wherein you have a surface in which the field variable is equal to T infinity everywhere, in this case the temperature, for t less than 0, and at t is equal to 0 the temperature is instantaneously increased to a value of T naught at the surface. And this is an infinite medium. Since we do not have a length scale in this medium, we obtained a similarity transform. Okay. The only variable that we could get was z by root of alpha t, okay, that is a similarity variable. And using that similarity variable, we had obtained a solution which was an error function. Okay. The solution for the scale temperature was an error function. Okay. So, it was an error function of this type. And after getting that solution, I had solved a problem for you for obtaining the thermal diffusivity and conductivity of a fluid from a temperature measurement, assuming that the medium was infinite. And we were now examining the diffusion into a liquid film, okay, the diffusion into a liquid film. I have a liquid film of say length L and thickness H, okay, falling down a wall, and it is brought into contact with a gas phase, okay, this contact with a gas phase in which one of the constituents, one of the solutes is dissolving into the liquid film. Okay. The contacting starts at x is equal to 0, where x is the streamwise coordinate. The coordinate z is the cross stream coordinate measured from the interface. Okay. The coordinate z is the cross stream coordinate measured from the interface. Okay. And I was considering the case where the penetration depth is small compared to the film thickness. We will come back and examine under what conditions is the penetration depth small compared to the film thickness, but that was the case that I was considering over here. Okay. So, this same zx coordinate, okay, I can transform it, okay, if I just invert it a little bit. Okay. So, this same interface here, okay, this is the interface, that the same, this is the interface, okay, and the z coordinate is measured from here, z coordinate is measured from here, okay, and this is C is equal to Cs at the surface, okay, and C is equal to 0 far from the surface. Okay. If I look at the progress of this volume element of fluid as it goes down, right, when it has traveled a distance x along the flow, it has been exposed to the gas for a time which is x by V max, where V max is the maximum velocity at the surface. Okay. So, it has been exposed, it is a constant velocity close to the surface, because the solution for the velocity profile is a parabolic profile which has a 0 slope at the surface, and therefore, close to the surface over a distance small compared to the thickness, the velocity can be considered a constant. Okay. So, I have a constant velocity parcel of fluid which is travelling downwards, and it has been exposed to the gas film for a time t, right, which is given by x by V max, where x is the distance from the start of the contacting section and V max is the maximum velocity at the surface. Okay. If it has been exposed for a time x by V max, then the solution, okay, for a diffusion into an infinite medium, if I neglect streamwise diffusion, okay, if I consider only diffusion perpendicular to the surface, okay, because there is diffusion perpendicular to the surface that transports material into the liquid film. So, if I neglect streamwise diffusion and consider only diffusion perpendicular to the surface, then this is equivalent to diffusion into an infinite medium after a time t is equal to x by V max of exposure, after an exposure time t is equal to x by V max. Okay. So, therefore, the solution is C by Cs, okay. C naught in this C infinity in this case is equal to 0. Okay. So, the solution is C by Cs is equal to 1 minus error function of z by 2 root dt, okay, where t is given by dx by V max. Okay. That is the solution for the concentration field. Okay. And we know for a parabolic profile, okay, we had calculated this when we did the flow down an inclined plane. V max is equal to 3 by 2 times the average velocity, okay, is equal to 1.5 times the average velocity for a parabolic flow in a plane geometry. Okay. So, because of that I can straight away get the concentration profile for this case under the assumption that the penetration depth is small compared to the film thickness. We will come back and examine the conditions under which that assumption is valid. So, I have C by Cs is equal to, or let me just write for the concentration field, C is equal to Cs into 1 minus error function minus z, sorry, plus z. What is the flux at the surface? Okay. Jz is equal to minus d times dcs by dz, okay, is equal to minus d okay, into Cs, okay, and by okay, using chain rule for differentiation, okay, express z in terms of psi, and this is the solution that you will get. The flux at the interface, okay, the flux at z is equal to 0 is equal to minus d Cs by okay, into 1 over root pi. Okay, the slope at 0 was equal to minus 1 by root pi, okay, because the slope at 0 of the error function is 1 over square root of pi. Okay. So, this is the solution for the flux at a given location x. Okay. This is a solution for the flux at a given location x. Okay. And we know that yeah, I am sorry, there should be no factor of 2 here, okay, because dcs by d psi, okay, so cs is equal, so psi is equal to z by root of dx by V max. Okay, so there is a transformation, okay, between Cs and psi. Okay, so yeah. Now you can see that this diffusion, this flux depends upon x. This flux depends upon x. Okay. So, it is a function of the downstream location. Okay. So, this is equal to dCs by root of d pi dx by V max. Okay. And if I express V max in terms of the average velocity, okay, if I express V max in the average velocity using this relation, I will get this as dCs by root of pi d, okay, x into V max will be by 3 by 2 V average. Okay, Vx by V max is 3 by 2 times V average. So, if I express in terms of the average velocity, this is what I will get. Okay. Now, the average flux J average, okay, is equal to 1 over L integral 0 to L dx times J z at the location x. Okay. The average flux is equal to the average over the downstream locations, okay, starting from the start of the contacting section all the way till the length L here. Okay. So, the average over the entire length L. Okay. So, that is the average flux. Okay. The only term that depends upon x in this entire relation is 1 over square root of x. Okay. So, I can take out all of the other terms, okay, out of the integral. I will get dCs by root of pi d, okay, into this 3 by 2 V average will go in the numerator, 3 V average by 2 integral dx times 1 by x power half. The integral of 1 over x power half is 2 times x power plus half. Okay. Integral of 1 over integral of x power minus half is x power half by half, which is 2 times x power half. Okay. So, this will turn out to be equal to dCs by root of pi times d root of 3 V average by 2, okay, and I will get 1 over L times 2 L power half. And you can easily simplify this, and you will get this is equal to root of 6 by pi, okay, d Cs by L into the VAV, okay, into L by d whole power half. Okay. You can easily verify that this is equivalent to this, because I have a V average times L by d power half, that is V average power half, d power half from the denominator here, okay, and the total power of L here is L power minus half, which is 1 over L into L power plus half. You can easily verify the two are equivalent. The reason I have written this in this form, because this is equal to root of 6 by pi into d Cs by L into the Peckley number based upon the length power half. Okay. Average velocity times length by the diffusion coefficient is a Peckley number based upon the length of the contactor. Okay. Okay. So, that is the final expression for the average flux. Okay. JAV is equal to root of 6 by pi, okay, into dCs by L into PE power half, the Peckley number based upon the length, not the thickness of the contactor. If I define a Sherwood number based upon the length, okay, Sherwood number based upon the length, okay, recall that the Sherwood number is the scaled flux. Okay, the Sherwood number is the scaled flux J average by d Cs by L. Okay. This is equal to root of 6 by pi times PEL power half. Okay. And if I evaluate this constant, I get a correlation 1.38 times PEL power half. That is a Sherwood number correlation for the diffusion into a falling film. Okay, that is a Sherwood number correlation for the diffusion into a falling film. Okay. Usually the Sherwood number is expressed not in terms of the length, but in terms of the thickness of the film. Okay. In this case, if the penetration depth is small compared to the thickness, physically the thickness is not a parameter, okay, but usually in these kinds of correlations it is expressed in terms of the thickness of the film. Okay. So, the actual Sherwood number when based in terms of the thickness will be equal to JV by dCs by H. Okay. Okay, so, that would be the Sherwood number based upon the thickness, okay, which is equal to H by L. I should first put is equal to root of 6 by pi H by L into VAV L by D whole power half. Okay. Just substituting for J average from here, and I am using the Peckley number VAV L by D whole power half. Okay. So, this I can write it as root of 6 by pi, okay, H by L power half into VAV H by D power half. Okay. You are just rearranging the terms, and this you can easily verify. This is just equal to 1.38 times PE power half into H by L power half. Okay, so, the Sherwood number based upon thickness goes as Peckley number based on thickness power half, okay, times H by L power half. Okay, so, when it is expressed in terms of H, whereas if you express it in terms of L, it is just the Peckley number. Okay, there is no dependence on H. Okay. So, this is the Sherwood number correlation. Okay, so, we have derived a correlation using a similarity transform for the mass diffusion into a falling film. Okay, so, this is the Sherwood number correlation. Okay. Of course, this correlation has its limitations. It is applicable only when the penetration depth is small compared to the film thickness. Okay. This is applicable only when the penetration depth is small compared to the film thickness. What is the condition for that to be valid? Okay. The penetration depth, if you recall, at a distance L, it is equal to L by V max. I am sorry, the penetration depth at a distance L, okay, the characteristic length scale at a distance L is this one. Okay. Okay. So, the penetration depth is D times L by V max, okay, has to be much smaller than H, okay, D L by V max power half. The penetration depth is the denominator of this, okay, d L by V max whole to the half, okay, at a distance x, at a time which is comparable to L by V max. Okay. So, there is the penetration depth at time t. At time t, at a distance L, the time of exposure is L by V max, and therefore, this is the condition for the, this is the penetration depth, okay, the denominator of this equation, square root of dt, where t has been expressed as L by V max. Okay. That is the penetration depth at a distance L downstream from the start of the contacting section. This has to be much smaller than L, okay, which means that d L by 3 by 2 V average whole power half is very much less than H. Okay. Just writing V as 3 by 2 times V average. Okay. So, that is the penetration depth in terms of the average velocity, okay, or 2 d L by 3 V average is much smaller than H square, okay, dividing on both sides by squaring both sides, getting the square of both sides. Okay. And if I divide both sides by H and I take the V average and D to the right side, I will get that L by H is much smaller than 3 V average H by D. by 2d. Okay. Multiplying by 3 V average, dividing by 2d and h. Okay. So, this is what I will get. Okay. And this is equivalent to 3 by 2 times the Peclet number. Okay. So, L by h has to be much smaller than 3 by 2 times the Peclet number for this assumption that the penetration depth into the film is small compared to the total thickness of the film, so that I can assume that it is effectively diffusion into an infinite medium. Okay. So, that is the condition for the assumption that this can be approximated as diffusion into an infinite medium. How valid is this? Okay. So, let us take some typical example, okay, some typical values. Okay. If I take V average, okay, as a very small value, okay, so I will take it as 10 power minus 3 meters per second, a millimeter a second approximately, okay, and h is equal to 10 power minus 3 meters, 1 millimeter thickness film moving at a velocity of 1 millimeter a second. Okay. So, this is the lower limit of the velocity and thickness you would have in practical applications. The diffusion coefficient I said was equal to 10 power minus 9, okay, 10 power minus 9 meters square per second, okay, for small molecules in liquids. Okay. And for this, the Peclet number is equal to 10 power minus 3 meters per second into 10 power minus 3 meters divided by 10 power minus 9 meters square per second, okay, which is equal to 1000 in this case. Okay. So, this approximation is valid so long as L by h is less than 1000 or so, okay, or less than a meter or so. If the velocity is larger, then this approximation becomes valid even for larger velocities. Okay. And for example, we had solved the problem of flow down an inclined plane, and if you put in the conditions for that, you will find that the velocity for a 1 millimeter film of water down an inclined plane is about 3 meters a second. Okay. So, in that case this ratio becomes even much larger. Okay. So, let us take a concrete example in order to illustrate this. Okay. So, I have a film, okay, in which there is gas diffusion of length L and thickness h. Okay. The average velocity is 2 meters per second, okay, and the thickness of the film, okay, h is equal to let us say a millimeter or so, okay, h is equal to 1 millimeter, and I have a concentration Cs at the surface of some solvent. Okay. Cs of a solute at the surface is given by 40 milligrams per liter. Okay. So, that is a surface, the equilibrium concentration of the pollutant at the surface, and I would want that the average concentration at the outlet, okay, at x is equal to L. Okay. If I take this as Z and this as x, okay, I want to dissolve, okay, an amount of the solute of the pollutant of average concentration 5 milligrams per liter at the outlet. Okay. And I want to know what is the length of the reactor required, or the length of the falling film that is required, the contactor that is required in order to achieve this, okay, average concentration at the outlet, okay, for a film of thickness h. Okay. So, what is the total mass of material that is coming out? Okay. So, if I have a film of length L, thickness h, and I assume that in the direction perpendicular to the plane, okay, the width is w. Okay. If you look at the material that is coming out at the end, it has an average concentration C average. Okay. The material coming out at the end has an average concentration which is C average. So, the total mass of material coming out per unit time at the outlet, right, the total mass of the material per unit time. Okay. Okay. This is going to be equal to C average times the cross sectional area, okay, into W into H, okay, into the average velocity. Okay. So, that is the total mass coming out per unit time, which is coming out at the outlet. Okay. That is the desired total mass out per unit time. This has to be equal to the total amount of material that is absorbed over the entire film. Okay. The total amount of material that is absorbed over the entire film is the average flux into the cross sectional area of the film. Okay. The total amount that is absorbed is equal to the average flux times the cross sectional area of the film, the surface area of the interface. The surface area of the interface of height L and width W is going to be equal to this into W into L. So, these two have to be equal. Okay. You can just equate these two, okay, and you will find that the average flux, okay, has to be equal to C average V average into H by L. Okay. That has to be the average flux. Okay. This average flux has to be equal to that which is given by the correlation. Okay. Recall that the correlation we had for the average flux was G average is equal to 1.38, okay, into D into Cs, okay, by L into VAV L by D per half, okay, when expressed in terms of PEL. Okay. Okay, that was the expression for the average flux when expressed in terms of the Peckley number based upon L. I will just use root of 6 by pi here, so that it is easier. And this has to be equal to C average, V average, H by L. Okay, and I can easily solve this equation. Just by substituting here. Okay. All quantities in this equation are known except for L. Okay. So, I can solve this equation for L. What I will get is that L is equal to pi by 6 into C average square by Cs square, okay, into V average H square by T, and you can easily verify that this has dimensions of length. Okay. Substituting the values, pi by 6 into C average square was 5 milligrams per liter whole square, Cs square was 40 milligrams per liter whole square. V average was 0.2 meters per second into H was 1 millimeter, that is 10 power minus 3 meters the whole square, divided by the diffusion coefficient. Okay. In this particular case, the diffusion coefficient is equal to 1.6 into 10 power minus 9 meter square per second. Okay. I told you that diffusion coefficient for gas, for small molecules in liquids is of the order of 10 power minus 9 meter square per second. Okay. So, this diffusion coefficient is 1.6 . Okay. And finally, the result that you will get is the height is about 1.02 meters. Okay. So, you require a height of about a meter in order to dissolve sufficient gas that the outlet concentration, you are removing 5 milligrams per liter at the outlet, or the total mass at the outlet will be equal to this 5 milligrams per liter times the width times the height times the average velocity. Height is 1 millimeter 10 power minus 3, average velocity is 0.2 meters per second. So, you get 2 into 10 power minus 4 into the width into this average concentration 5 milligrams per liter. Okay. So, that is the length that is required, okay, for achieving the design objective of removing sufficient gas at the outlet. Okay. So, this is an example where we had actually used a similarity solution to get an analytical result for the average flux, to get a correlation for the average flux. That correlation had a constant square root of 6 by pi, which is approximately 1.38. So, that is how you get those constants in those correlations, okay, and the dependence on the Peclet number. When expressed in terms of the Peclet number based upon length, it is just PEL per half. That is because the penetration depth is much smaller than the film thickness, and therefore, the thickness is not a parameter. However, if you express it in terms of the Peclet number based upon thickness, then you will get this kind of a result. Okay. And I had demonstrated to you how this can be used to actually design a contactor for achieving a specific objective of dissolution of a gas into the liquid film. So, this is for diffusion into an infinite medium. Okay. So, next class I will start on another kind of diffusion into an infinite medium, not where the field variable is fixed at the boundary, but rather when you inject a certain amount of material or heat into the medium. That we will examine in the next lecture. I will see you then.